Hi, this clip is a part of the lecture on the analysis of statically determinate arch. I'm going to demonstrate you how to solve to determine the reaction and the moment of the arch structure as shown. And this arch it has the internal hinge at D, so this hinge at D, and it also has the A as the pin and the B as the pin, and is subjected to the force of P equal to 10 kilonewton. So this is gonna be 10 kilonewton, and F of 25 kilonewton and Q of 25 kilonewton. So this is also 25 kilonewton. Okay, and they like us, as I show on this table, to determine that kind of forces and moment. And as you may know from the lecture, this type of arch has pin, and hinge. We call this T hinges arch. Okay, it is a kind of statically determinate arch. But if you take a look, okay, by this, you may see for the whole arch, you're going to have the unknown force of A sub x, A sub y, B sub x, and B sub y, and we cannot solve it because the whole free body diagram have 4 unknowns. So by this type of hinge, we know that we're supposed to draw the free body diagram. First, we're going to draw the free body diagram of the segment AED and BCD by the lesson that I show you, and then we will determine the forces at the hinge and the forces at the support later. Okay, so the arch is kind of hard to draw the free body diagram. You got to copy it carefully. 1, 2, 3, 4. Okay, and this one gonna be 2.3. So you got to get this one of 1, 2, 3, 4, and another one is just 2.3. Make it carefully on this. Okay, and the other one, you have this for 2.4, and this is 2.4, right? This is 2.4, yeah, and this is gonna be 1.3. Okay, let's have this one for 1.3, 1.3, and then another one is going to be 2.4. So this is sketch of the arch. Okay, and this is the crown, okay, of the arch, and then you can draw this carefully to obtain a nice picture, even though it's not the same, but let it as much as neat and as beautiful we can. Okay, we have this one for the A, this one for the D, this one for the D, and this one for the B, and you also have this one for the B. That is 9. Okay, that is 9. If we put this 9, and then the next you're going to get it vertically. This is going to be the E. Okay, and also this is going to be about 12, half of this. So you got to put this one. This is 15, this is 12, and you put the force here. And this is going to be the no force of 25 kilonewton, and this is going to be C. And also we have this one is 10 kilonewton, and this one is going to be 25 kilonewton. And you also have the reaction. This is going to be the A sub y, and this is going to be the A sub x. Okay, and also here you're going to have the B sub y, and you have this for the B sub x, and you still have what the hinge, okay, at the D. So push the hinge of this one by the third law of Newton. It's going to be in the opposite direction. And for the D sub y, if you put this is downward, it's going to be upward D sub y. And then we have some of the important length must to put in. This is going to be 12 meter, 36 meter. This is going to be 14 meter, 14 meter. And the author you have is 16 and 8. Okay, just put this one and put this one. You got this is for 8 meter. It's not like kind of scaling. Okay, but it's quite good though. And then you have this is the distance of 12 meter. Okay, just put this one. This is going to be 12 meter, and this one is going to be 10 meter. 10 meter. And since this one is 12, 10 and 12 is 22, this one is 24, so you can take this for 2 meter. Okay, that is our free body diagram of the segment A, E, D and B, C, D. And the second. Okay, use the equation of equilibrium to find, we choose which one first. We find d sub x and d sub y and a sub x, a sub y, b sub x and b sub y. So, okay, and then that's we should use this free body diagram to determine it. And then let us consider the free body diagram. Consider the free body diagram of segment AED, segment AED. Okay, if you do that, you're gonna get what? Take the moment of A. Okay, you do the summation of the moment at A equal to 0, and then let counterclockwise as positive. So take moment here. You got the d sub y times 48, and clockwise that is negative, and d sub x gonna have line of action here and have the moment arm between this and this is 14, and it's going to rotate counterclockwise, so it's going to be plus what? Plus d sub x. Okay, and d sub x have line of action here is going to time 14, so 14. And how about d sub y? D sub y is a kind of in the opposite direction. So it's going to be minus d sub y. And this is going to be 48. And also, what do we have? The 35. The d sub y rotates like this. 35 also does like this. So it's going to be minus 25 minus 25. And 25 going to time 12. Okay. And then what? We have what? We have 10. The 10 also trying to rotate this. So you're going to have minus 10. And then you got to time what? The 10. The 10 is up here. The height over here is 16. So times 16 equal to 0. Okay, and then if you write it clearer, you will get this is what the d sub x times 14. Okay, and no, it's not a 14, it's going to be 24, sorry. That's 24. This is also of 24. And then you will get this one for 24 d sub x and minus 48 d sub y. And you put this 12 times 25 is going to be 300, right? Okay. And then it's going to be 300. And this is 160. So it's going to be 460. And this is going to be first equation. Okay, and on the other side, you may consider the free body diagram. Consider the free body diagram of segment. This one, BCD. Okay, and do it again. You may summation of moment equal to 0. Do the summation of moment about B equal to 0. And this time just put it clockwise as positive. Okay, you take moment here and you can see that d sub x gonna have line of action here, and it's going to have this for 12 meter. Okay, and it's gonna rotate clockwise. D sub y also gonna rotate clockwise with 28. So both of them gonna be plus. So the d sub x is here. The d sub x is here, and it's gonna time 12. And the same direction plus d sub y. And d sub y have a line of action here, so it's gonna time this is gonna time 28. Okay, and what else do we have? Taking moment about here, we have this one. Have the moment arm time 14, and it's going to be rotated in opposite direction, so equal to 25 and gonna time 14. So this one we have 12 d sub x plus 28 d sub y equal to 350, and that is going to be equation 2. Okay, to solve this we may rewrite this equation to be a simple one. Let's make this guy like d sub x equal to when you put this across, it's going to be 48 d sub y, 48 d sub y plus 460, and then you're going to divide it by 24, right? And if you do this, the d sub x going to be equal to, this is 2 d sub y, and this going to plus 460 divided by 24, 19.167. Okay, and then you plug this equation back into this, so you're going to get this one for 12 times 2 d sub y plus 19.167. Okay, and then you may plus 28, and then d sub y, and then you get is equal to 350, and then you can rearrange. See, this is going to be 24 d sub y plus 28 d sub y, and this is going to be time. Okay, that's you're going to have 24 d sub y plus 28 d sub y, and then you're going to get 350, and then what you have is going to be minus 12 times 19.167, and now if you sum up everything, you will get d sub y equal to, this one is going to be, if I'm correct, 119.996, and then divided by 24, and 28 is going to be 52, and then you get this for 2.308 kilonewton, or 2.31 if you like. Okay, the d sub y is gonna be 2.31 kilonewton equal to d sub y, and then if you plug this one back here, your d sub x is gonna equal to 2 times 2.308, and then plus 19.167, and then you get d sub x of 23.783 kilonewton. Okay, you get this of 23.383. This is going to be equal to 23.78 kilonewton. Okay, that's you get only the force at the hinge, and you didn't have the reaction yet. So next we gonna move up a little bit and use the equation of equilibrium to determine the reaction. Okay, find determine. Let's set determine the reactions. Okay, of a sub x, a sub y, b sub x, and b sub y, and then you still use the equation of equilibrium summation of x sub x equal to 0. Use the free body diagram of this segment, and then you put this, because the a sub x is in this direction, so you get the a sub x, and by this is 10, right? Plus 10, a sub x plus 10, and then this is going to be in opposite, equal to 23.78, and then your a sub x gonna be 23.78 minus 10 is going to be 13.78 kilo Newton. Okay, and the last one, you just do the summation of f sub y equal to 0. Summation of f sub y equal to 0. You're going to find what? The a sub y. So put this one up, right? You're going to have the a sub y up, and then minus 25 minus 2.31, and then it's going to be equal to 0. And if you put this, your a sub y is going to equal to how much kilonewton? A sub y going to be 27.31 kilonewton. Okay, and then that is for the a sub x and a sub y. And then we have the order for this one, and we gonna determine the b sub x and b sub y. So again, summation of x sub x equal to 0. This time b sub x, this is plus. So you get the b sub x equal to this one, 23.78. So this one gonna be equal to, there is no also force, 23.78 kilonewton. So and the last one, you do the same, summation of f sub y equal to 0. B sub y is up, so up is plus. We have the b sub y up, d sub y plus 2.31. Okay, and then 25 is downward, equal to 25. So if you do that, the b sub y gonna be equal to what? 25 minus 2.31 is going to be 22.69 kilonewton. Okay, you got this, all of the reaction. And if you may consider these forces are the component of the resultant force as A, and this also the resultant of force at B. And if you do the scaling, okay, let's see, this is 13.78 and divided by 2, that's about 7 millimeter. That is about 7 millimeter. Okay, and the a sub y about 28, that is going to be 14 millimeter. Okay, and then this is 27.31 kilonewton, and this is going to 13.78. This is 13.78 kilonewton. You got this, and this is going to be 23.78. That's 24 divided by 2, about 12 millimeter. Okay, let's put it 23.78. This is 23.78 kilonewton, and this is divided by 2, about 11 or 12 millimeter. This, okay, and this is to be 22.69. This is 22.69 kilonewton. And what we have now is we put these forces on scale. In order what, if you put here, we can do the zooming a little bit. What we have is by doing the scaling, and then you can project this one, and then you project this one and project this one. What you have is you're going to have the resultant force at the A. Okay, this is going to be resultant force of A, and it's going to be what? It's going to be square root of, so it's going to be the square root of 13.78 square plus 27.31 square, and you just put it like this, and the R sub A is going to be 23.89. This is 23.89 kilonewton. This is the resultant force that you use to design the foundation, design the hinge at A. Okay, this is going to be R sub A. For the R sub B, and you see it's going to be over here, and this is going to be R sub B, and R sub B is going to be equal to the square root of 23.78 square plus 22.69 square. Then you get this. The R sub B, when you put them, you may get this one for 32.87 kilonewton, and you may see this is going to be the maximum compressive force, okay, on the arch, on this arch, on acting on this arch. Okay, this is going to be the maximum one. So let me put the highlight on this. This is going to be the maximum force on this. Okay, and if you like, you may have this chance to put the A sub x is 13.78 kilonewton. Direction is to the right. A sub y is upward, 27.31 kilonewton upward, and B sub x is 23.78 kilonewton to the left, and this one is going to be 22.69 kilonewton upward. Okay, you all have all the forces, and you see the required resultant force that's used to design the support and the foundation. Next, they ask us to determine the M sub E. Okay, what the M sub E is going to be on the portion of this, and that means we're going to draw the free body diagram of that portion and determine the moment at point T. So let me project this point. Usually, to draw the free body diagram effectively, just do the projection. Okay, take this one and take this one, and you will see this is going to be 12 millimeter. So if you mark this is going to be 12 millimeter, and you measure this is going to be the element AE. This is E, this is the A. Okay, and you may have what? You may have 23.31. This is going to be 27.31 kilonewton, and you also have the compression here of 13.78 kilonewton, and at point E you have 10 kilonewton and 25 kilonewton, so this is gonna be 25 kilonewton, and this is gonna be the 10 kilonewton. This is 10 kilonewton, and you have this for 16 meter, this length, and this length 16, and this is 12. This is 12 meter. That is going to be the free body diagram of this part. Okay, and if you like, you can find the unknown forces. Let's put the unknown force here. That is going to be the N sub E. And also perpendicular to it. It need to be perpendicular. It's going to be V sub E. They are perpendicular to each other. And then we have this one, the moment of M sub E. Okay. And before that, let me put some additional cut into this portion, and then later we will use the equation of equilibrium to determine both of them. This is going to be what? This is going to be 10 millimeter, and this is going to be 12. So this is 12. This is 10 millimeter. So this is point C, this is point B, and then you get this one to be the curve of the arch like this. And again, this have 23.78. So you have this for 23.78 kilonewton. And the upward is going to be 22.69 kilonewton. And at this point C, we have 25 kilonewton. 5 kilonewton. And then again, you have what? You have the compression here. Okay, and don't forget, it's going to be perpendicular to it. That's it's going to be the N sub C and the V sub C. And you can have this one for the M sub C. And you may see we cannot find the shear force and the normal force since we don't know the angle. Okay, we only can find it if we know the angle because it's not in the XY axis. Okay, let we consider this one first. To determine the M sub E, we got to take the moment at this point to eliminate all the forces here. So summation of moment of E equal to 0, and let this direction as the positive. So this M sub E gonna be what? M sub E. M sub E rotate like this. Okay, this guy gonna rotate in the opposite direction. This guy gonna to rotate in the same direction. So it's gonna be plus 13.78, and this one have the moment arm here, so times 16. The other direction, the same direction, right? The same, and it's going to be equal to what? This is the direction. This one 27.31, 27.31, and 27.31 is going to be times this is 12. Okay, and if you do the calculation, you will get M sub E equal to 107.24 kilonewton meter. Okay, that is for this part. Okay, but for this is the summation of moment at C equal to 0. And now this time M sub C is like this, is plus. So M sub C equal to what? Take the moment at the C, and then this one going to be up, right? And going to rotate in the opposite direction with this moment arm of 14 meter. Okay, and this one of 10 meter. You may have this gonna be here times 14. So it's gonna have 22.69 times 14. Okay, this one is in this direction, this one was the direction, but this one gonna be in the same direction of this, and this one have this moment arm of 10, and if you put it, it's going to be plus, but when you put this one, it's going to be minus 23.78, and this time is here. This time, this one for 10 meter. Okay, this one going to time 10. And if you put everything again, you will get m sub c of something kilonewton meter. That's going to be 34.48. Okay, that's all we have for the analysis of this three-hinged arch. This arch is not parabolic, it's not circular, or it's not cantilever shape. It's kind of in any shape. Okay, we don't know it because the problem statement didn't tell us anything about that. And then for this, we have the m sub e of 107.24 kilonewton meter, and it's rotated counterclockwise, as you may know in my finger here. Okay, the three-hinged arch, we cannot use the free body diagram of the whole arch because there are 4 unknown forces here, so we separate into 2 segments, and the unknown changing from 4 to 6, and we have the equation of equilibrium of 3 plus 3 is 6, so this is the statically determinate arch. And then we solve it by taking the moment at A to obtain this first equation of d sub x and d sub y. And then we take moment at E, we got the second equation of the force of d sub x and d sub y, and then we solve it, we get the d sub x here and also d sub y here, and then this is d sub y, this is d sub x. And following this, we can determine the reaction as required us to do so. From this problem, we got the reaction of a sub x and a sub y, and then if we put this, it's going to be a sub x and a sub y, and it also has this one for b sub x and b sub y, and then we put it for b sub x and b sub y, and then we determine the resultant force, and we find the maximum compressive force of 32.87 there. Okay, and we also can find the moment that occur in this portion. This portion is the pink portion, let's say. Okay, and also this one, and we also can determine the moment for m sub c, and it's going to be this. Okay, and finally, if you like to design the foundation, you may need, or you may require to determine the angle that's the resultant force at theta A here, and also the theta B here. Okay, and you may see that if you like to find tan theta A gonna be this vertical divided by this horizontal, is gonna be 27.31, and then it's gonna be divided by 13.78, so this is y equal to 13.78, so you may get theta A of 63.2 degree. And for this, do the same. The vertical is 22.69, so tan theta B equal to 22.69, and this is a vertical, right? And divided by the horizontal of 23.78, and then you get the angle of theta B equal to 43.7 degree. And that is important because your foundation supposed to taking care of the maximum resultant force at this angle and another maximum force at this angle. Okay, that is all this problem. I hope you guys will watch these clips and then try to work this problem by yourself, and you can develop the skill to analyze the structure manually. Okay, that's it.